Проверим индикацию течи с помощью проверенного течеискателя Улвак-Гелиод. Оба наши прибора настроены на индикацию в миллибар-литр в секундах. И спустя некоторое время стабилизации мы видим, что наш поток равен примерно 4 на 10 минус 4 миллибар-литр в секунду. Удаляем щуп из течи. И мы видим, что поток возвращается к нашим фоновым значениям в зеленую зону индикации.
После монтажа любой трубопроводной системы возникает вопрос о проверке ее герметичности и надежности. Меня зовут Александр, и сегодня я расскажу вам, как работать с опрессовочным насосом. Компания Ротенбергер представляет широкий ассортимент ручных и электрических опрессовочных насосов для проверки герметичности отопительных систем, а также систем водоснабжения. Ручные насосы позволяют нагнетать проверочное давление до 60 бар. Максимальная вместимость резервуара для воды 12 литров. Плунжерный рычаг ручного опрессовщика можно использовать как переноску, что весьма удобно и практично в работе. Проверка на герметичность осуществляется путем создания проверочного давления, которое в 1,5 раза выше рабочего. К проверяемой системе подсоединяется опрессовщик. Система заполняется водой, выпускаются воздушные пробки и производится закачивание. По манометру контролируется давление. Падение давления в системе говорит о негерметичности системы и наличии утечки. После обнаружения и устранения утечки система опрессовывается повторно.
Dye penetrant examination is an important method of non-destructive testing of materials. This is the basic principle. Often the surface of a workpiece is covered with rust or paint, which masks the material defects, as shown in the sectional view. Therefore, the first step is always the pre-cleaning of the test piece surface. This must be done very thoroughly so that any defects present, here it is a crack, are open to the surface. In the second step, the penetrant is applied to the test piece, usually a red-colored low-viscosity oil. Due to the penetrant's high surface wetting capability, it penetrates into the defects and cracks. After several minutes of dwell time, the third step is to rinse the part's surface cautiously with water. The water removes the penetrant completely from the surface, but leaves it in the crack. Now, the fourth step. After drying the test piece, a developer is applied onto the surface. The developer is a fine-grained white powder suspended in a liquid. It forms an even coating on the surface. After drying, it draws penetrant from the crack out onto the surface. The location of the crack is indicated clearly on the surface. And this is how it is carried out in practice. We wish to inspect two samples, a segment of a worm gear shaft and a broken bicycle crank arm. Both test pieces have already been cleaned. First in line is the worm gear shaft. The material tester applies the penetrant. After a dwell time of about 10 minutes, she removes the excess penetrant from the surface by rinsing the test piece gently with water. She takes care not to rinse for an unnecessary long time because the penetrant is supposed to stay in the defects. Now she dries the surface of the sample with a cloth to absorb the excess water. As the final step, she applies the developer and lets it dry. That's it. Several cracks are indicated on the surface in deep red color. Next, the broken bicycle crank arm has to undergo the dye penetration test. Spraying with penetrant, allowing to soak, rinsing, drying, and applying developer. Clearly, additional cracks are indicated on the fragments. Non-destructive testing. Ultrasonic examination. The basic principle of ultrasonic testing of materials is the propagation and reflection of sound waves. As an example, a cylindrical workpiece is shown in the animation. The longitudinal section through the cylinder shows the position of the atoms, extremely magnified and simplified as a single crystal. To begin with, a rigid unyielding stop is attached to the right front end of the cylinder. At the left front end, a disc is installed. It will be used to transmit and receive sound waves. Pushing and pulling briefly at the disc causes a longitudinal sound wave to propagate through the cylinder. When the sound wave reaches the rigid stop at the right side, it is reflected and runs back towards the disc, which now serves as a receiver. A free end is also able to reflect a wave. In this case, however, the tensile side runs ahead in the reflected wave and finally deflects the receiver to the right. The reflected wave is even reflected again and actually travels for several times across the length of the cylinder, but this is not shown in the animation for the sake of simplicity. So, if a sound wave is generated at one end of a workpiece, it will travel through the material with its speed of sound. At the free end of the workpiece, the sound wave is reflected and it returns to the transmitter, which then acts as a receiver. For ultrasonic testing of a workpiece, not a large transmitter is used in most cases, but a rather compact one, which generates a short ultrasonic pulse. At a place free from defects, the ultrasonic pulse travels to the right front end, also termed back wall. The pulse is reflected and recorded again as an echo. When the transmitter is moved a little downwards, the cavity reflects a part of the wave. That part arrives earlier at the transmitter than the rest of the sound wave. Even further downwards, the cavity reflects the complete ultrasonic pulse. For material testing, either the echo of a defect can be utilized, this is the pulse echo mode, or the phenomenon that hardly any sound waves pass through the imperfection, this is called the through transmission mode. In pulse echo mode, a transducer installed in a probe performs both the sending and the receiving of the ultrasonic pulse. On a computer monitor, the intensity is being plotted upwards on the y-axis and the time towards the right on the x-axis. With the probe at a place free from defects, only two signals may be seen on the monitor: the transmission pulse and the echo resulting from the lower surface of the workpiece, termed back wall echo. Moving the probe towards the right leads to an additional echo created by the defect. Even further towards the right, only the defect echo is visible apart from the transmission pulse. In our laboratory, there's a green painted steel cylinder to be found. It contains artificial defects which are invisible from the outside. To track down the defects, the material tester uses the pulse echo method. This is how a typical probe looks like. Under the bright wear plate, a piezoelectric disc is installed. It can transmit and receive ultrasonic pulses. A computer operates the probe via a plug-in card and power electronics. On the monitor, the intensity is plotted upwards and the time is plotted to the right. After placing the probe on top of the cylinder, initially no echo at all may be seen on the monitor. The reason for this is the too small contact area between the probe and the workpiece. Only with the use of a gel, the so-called couplant, the ultrasonic pulses can get into the workpiece and can also go back into the probe. Now the back wall echo turns up on the monitor. The material tester spreads out the gel evenly on the top surface. That way she is able to examine the entire cylinder. Using the velocity of sound in the material, one can plot the calculated depth on the monitor to the right instead of time. A very useful feature. With the help of so-called trigger gates, which may be set on the echoes with a computer mouse, the depth of the defects can easily be read off at the lower left-hand corner of the monitor. The cylinder back wall lies in a depth of about 200 mm below the probe, so the cylinder has a height of 200 mm. And here we go. The material tester scans the upper front end of the cylinder with a probe and observes the monitor. A defect echo appears on the monitor. This defect is located in a depth of 130 mm below the surface. Another echo indicates a defect in a depth of 87 mm. The second smaller echo at 174 mm is caused by double reflection on the same imperfection. And these are the defects: a drill hole and a saw cut. Filled up near the surface and painted, they are not visible from the outside. The drill hole in a depth of 130 mm. The saw cut 87 mm below the surface. Trams are popular means of transport in Karlsruhe in southern Germany. The tram cars are not only cleaned regularly, but also tested thoroughly in regular intervals by the transport company. Among many other maintenance points, the ultrasonic examination of the wheel axles plays an important role. A tram enters the maintenance hall for inspection. Some of the tram cars have already been lifted up. That way the bogies can easily be detached, pushed forward and examined carefully. This is one of the bogies, jacked up to comfortable working height and prepared for ultrasonic inspection. Special attention is given to the wheel axle, among experts known as wheel set axle. It has been designed as a hollow axle. This saves weight and facilitates the ultrasonic examination. The material tester applies a suitable oil as a couplant into the bore of the axle. Now he takes a special probe designed exactly for this purpose, inserts it carefully into the bore with a mount, and evenly spreads out the couplant by turning and pushing. He has accurately marked the most important examination points at the mount. In an experienced manner, he positions the probe at the appropriate places within the wheel set axle and watches the monitor closely. The probe has specially been designed for this application. It transmits the ultrasonic pulses at an angle of 45 degrees. At a place without defects, no defect echo returns. But when the pulse encounters a crack which has grown in from the outside, double reflection occurs and a typical defect echo is recorded. It is important to note that also the shape of the wheel set axle may lead to an echo, for example at shoulders. These are so-called contour echoes. In this particular case, only contour echoes are recorded. No abnormality has been detected. The wheel set axle is perfect and can be used again to transport many passengers until the next examination becomes due.
Дефектоскоп ОСЕ-65ФР позволяет проводить контроль сварных швов и основного металла, выявление трещин на объектах промышленного производства, авиастроения, машиностроения, нефтехимической и других. В производстве непрерывно литых металлических заготовок и трубной арматуры, в строительстве и обслуживании нефтепроводов и металлических конструкций. Дефектоскоп ОСЕ-65ФР впервые совмещает использование классических преобразователей фар с математической обработкой сигналов по методу SAFT, в результате чего удалось с использованием стандартных 16-элементных преобразователей получить разрешающую способность и качество картинки, ранее доступны только на дорогих 32-канальных фазированных антенных решетках. ОСЕ-65ФР сочетает в себе все преимущества дефектоскопов на фазированных решетках: секторное S-скан и линейное L-скан сканирование, построение B-скана хода лучей с учетом толщины контролируемого материала, одновременное отображение на экране А, S и B-сканов для удобства работы оператора. Помимо традиционных функций, прибор ОСЕ-65ФР имеет вход двухкоординатного энкодера, позволяющего подключать различные сканеры для построения S, B и других сканов, а наличие конструктора сварного шва и режима учета реальной геометрии изделия позволяет сделать контроль удобным и наглядным. Возможность ОСЕ-65ФР работать с обычными ультразвуковыми преобразователями в режиме классического дефектоскопа.
Non-destructive testing, X-ray inspection and industrial computed tomography. X-ray inspection and computed tomography are widely used in many areas of everyday life. Their application is best known in medical imaging. Using X-rays, medical doctors can visualize the interior of the human body. Even complex structures can be made visible. But X-rays are not only used as a diagnostic tool. They also contribute to our security, for example at the airport. At the security gate, each piece of luggage is examined by X-rays, also the suitcase. The X-ray image of the suitcase looks like this. Various objects can be identified. An alarm clock, a pair of glasses, a hairdryer, a trouser hanger, a pair of shoes, and many other items. In contrast to conventional X-ray images, here the objects are displayed in colour, according to their specific material. This is made possible by distinguishing between low-energy and high-energy radiation. Metallic objects are displayed in the colour blue, certain non-metallic items in orange. In this way, it is easier to detect dangerous objects. X-rays are frequently used in non-destructive testing of materials as well. The inner contours of complicated workpieces can be made visible, and of course defects, such as cracks and pores. But how are X-rays actually produced? They are generated in a so-called X-ray tube. To build an X-ray tube, first of all a thin-walled glass tube with a high vacuum within is needed. In the lower part of the tube, a V-shaped wire made of tungsten is positioned. This is the so-called thermionic cathode. A cylinder with an inclined end face is located in the upper part of the tube. This cylinder is the anode. It is made of a refractory metal that conducts the heat well. From a high voltage source, the positive pole is connected to the anode, and the negative pole to the thermionic cathode. The thermionic cathode is now heated up by an electric current. The thermal movement enables some electrons inside the wire to leave the surface. This is known as thermionic emission. By switching on the high voltage, a strong electric field between the thermionic cathode and the anode is created. This strong electric field accelerates the emitted electrons towards the anode. An electron beam is formed. The electron beam collides with the anode at high velocity. The anode material slows down the electrons within a very short distance. This generates the desired X radiation, but unfortunately also a lot of heat, which has to be dissipated by cooling. Because the anode surface is slightly inclined, the emission of the X radiation towards the right is more intense, but a certain proportion also radiates in other directions. A protective housing shields X-rays going in unwanted directions. The desired X radiation can only reach the outside through a small transparent window. With this setup, a high-resolution X-ray examination is not yet possible. The problem here is the large area on the anode where X-rays are generated. The X radiation is too diffuse, so a fuzzy and low-contrast X-ray image would be the result. To solve the problem, an electromagnetic lens is used to focus the electron beam at a small spot on the anode surface. The smaller the focal spot, the sharper and higher in contrast the X-ray image will be. Now, how are X-ray images actually produced? For an easier understanding, we will first depict the usable X radiation as a grey cone, and then simplify it as a parallel beam. To take an X-ray image, a suitable image capture unit is needed. This can either be a conventional X-ray film which turns darker the higher the intensity of the radiation, or it can be a digital detector field that measures the intensity of the radiation and converts it to electrical signals. When the radiation intensity is plotted as a function of the position, a uniform distribution is the result, as shown here. At each point, the image capture unit records the same radiation intensity. But what happens to the diagram when a material sample is placed in the radiation path? The sample absorbs part of the X radiation. The principle is, the thicker the sample in the direction of beam propagation and the higher its density, the less radiation reaches the image capture unit. Defects such as cracks or pores absorb very little radiation. Therefore, places with defects lead to higher radiation intensity at the image capture unit than flawless places. Defects extended in beam propagation direction can be seen particularly well. Those defects which only have a small spatial extension in beam propagation direction can hardly be seen, or cannot be seen at all. And this is what the complete X-ray image of the sample looks like. The originally depicted sectional plane of the sample is shown as a dashed line. Places with defects appear darker because a more intense radiation reaches the image capture unit. As expected, the vertical crack is virtually undetectable. This X-ray image is only obtained with parallel radiation. Using a classical X-ray tube, however, the radiation is cone-shaped. The intensity distribution will therefore look different, and as a consequence, also the X-ray image. The edges of the sample now appear three-dimensionally and not as clearly outlined as before. But now there is another problem. The position of the defect in depth, that is, in beam propagation direction, cannot be determined with a single X-ray image alone. It hardly makes a difference in the image whether a defect in the sample is positioned further to the left or to the right. In order to determine the depth of location of a defect, at least one additional X-ray image has to be taken from a different direction. Computed tomography pursues exactly this approach, not only by taking one, but in fact many additional images. A fantastic method. How does it work? The aim of industrial computed tomography is to create a three-dimensional computer model of the sample. To explain the principle, we are going to examine a simple rectangular aluminium specimen. It is placed on a rotating sample stage. various saw cuts and drill holes have been machined into the specimen. The X-ray tube is located on the left side. The detector field is on the right-hand side. In step 1, the computer tomograph records one X-ray image after the other and saves it. After each recording, the sample stage rotates the specimen by a certain angle. In this way, many individual X-ray images from different directions are captured. In contrast to medical diagnostics, the X-ray tube and the detector field are both at rest, and the sample rotates. The X-ray images are displayed in real time on the computer monitor. As opposed to classical X-ray images, they are shown as positive images. Thick areas and areas free from defects now appear dark. Thinner regions or regions with defects appear light. The drill holes and the different saw cuts are clearly visible. After all the X-ray images have been taken, step 2 follows, the generation of the computer model. This step is called image reconstruction. For image reconstruction, several useful methods exist. Here we will explain a commonly used method, the filtered back projection. A specimen with a cube-shaped cavity is used here as an example. To demonstrate the principle, we will explain the back projection of a sectional plane that goes through the cavity. The sectional plane looks like this. After having taken all X-ray images, the distribution of the transmitted X radiation is projected back into the sectional plane. This process is repeated for each X-ray image and the distributions are superimposed. With each superposition, the quality of the model increases. Displayed as a positive image, the back-projected plane looks like this. Much better results can be achieved with appropriate filter methods and with even more images. The back projection is carried out successively for each sectional plane, until finally a three-dimensional model of the sample is generated by the computer. Using sophisticated visualization methods, the sample can be examined in detail on the computer display. This is the computer model of our aluminium sample. Not only can it be viewed from the outside, a look at the inside is also possible by means of various sections through the specimen. The first drill hole, the second drill hole, the saw cuts, and the third drill hole. And here we go. We want to examine part of a die-cast sample made of an aluminium alloy. Shortly after the start, the first X-ray images can already be seen on the monitor. After recording one X-ray image, the sample is rotated slightly and the next image is taken. The resulting X-ray image files are also called raw data sets. Later on, the raw data sets enable a reconstruction of the individual cross-sections and, based on them, the calculation of the computer model. Now the computer model is completed. The inside of the sample can now be inspected in detail, and above all, the method is completely non-destructive. Many pores of different sizes can be seen. The pores are filled with air that has been trapped in the course of the die casting process. The venting of the die has not been good and has led to a great number of large air inclusions. If preferred, the material can also be visualized transparently. Then the defect surfaces appear bright. The following image shows an enlarged section of the sample in red-green technology. With ordinary red-green glasses, the pores in the interior of the material can also be experienced in 3D. Computed tomography is a fantastic method, so it is not surprising that it is being used more and more as an excellent non-destructive testing method in materials testing.
Качество сварных соединений – один из краеугольных камней, на которых основана безопасная эксплуатация трубопроводов, постоянно работающих под давлением. На газовом месторождении тысячи сварных стыков. В надежности каждого нужна не просто уверенность, а гарантия того, что стык не подведет. Все соединения проходят обязательный контроль. Один из методов, который позволяет обнаруживать малейшие дефекты – рентгеногаммография.
Рентгеногаммография применяется для определения несплошностей внутри сварного соединения. Для определения таких дефектов, как газовые поры, шлаковые включения, скопление газовых пор, скопление шлаковых включений, для определения непроваров корней шва, трещин в сварном соединении.
Даже самый профессиональный сварщик при выполнении работы не застрахован от ошибок. Визуально определить качество сварного шва в большинстве случаев невозможно. Тут на помощь приходит современная наука и сложное оборудование. Принцип таков: сварное соединение просвечивают с помощью ионизирующего излучения.
Это вот дефектоскоп. Внутри там находится радиационная головка, скажем. Вот это подключили мы пульт. Вот это непосредственно ампулопровод. Мы его будем устанавливать на шов вот сюда.
Соблюдение правил техники безопасности – основа работы дефектоскописта. С ионизирующим излучением шутки плохи. И хотя современное оборудование обеспечивает безопасный уровень радиации даже в непосредственной близости от источника, тем не менее, нарушения норм охраны труда не допускаются ни при каких условиях.
Перед тем, как начать работу, мы непосредственно на объекте определяем радиационно опасную зону.
Вот начинает работать и запикал. Значит, источник здесь.
Такими приборами, как дозиметр и радиометры. У нас есть дозиметр и радиометр ДКС-04. Определяем расстояние безопасное.
Вот у нас 12 метров, но мы обычно все равно, когда включаем, там еще же нужно время, чтобы произошло экспонирование пленки. И мы отходим еще время экспозиции, мы еще даже немножечко сами отходим.
На границе этого расстояния мощность дозы излучения не должна превышать 10 микрозиверт. Это значит, переводя в миллиберы, это значит 1 миллибер в час.
Границы зоны безопасности ограждают сигнальной лентой и обозначают специальными знаками. Из зоны проведения работ удаляются все посторонние. И только после этого специалисты приступают к выполнению контроля качества сварных соединений.
Свинцовыми циферками набираем объект, число какое, номер стыкового соединения. И вот это все, у нас потом это все отображается на пленке.
И вешаем его под стыком. Вот. Пленка повешена. Теперь выставляем коллиматор наш. Да. Приводим аппарат в рабочее положение.
После того, как мы эти все операции провели, отходим на безопасное расстояние к дистанционному пульту и выводим радиационный источник в рабочее положение из радиационной головки.
Сейчас, когда мы все установили, все отошли оттуда и начинаем включать пультом наш дефектоскоп.
После того, как мы провели неразрушающий контроль, зависимо, подобрали время, соответственно, время экспозиции, какое там, выдержали это время экспозиции. После этого мы заводим источник ионизирующего излучения, конкретно мы его применяем сейчас, у нас иридий-192. Мы его заводим в радиационную головку. Собственно говоря, процесс контроля произведен.
Чтобы получить полную информацию, как правило, выполняют 3 экспонирования по всей окружности сварного соединения. Длительность зависит от толщины металла и мощности ионизирующего излучения. После проявки пленки в лаборатории имеем рентгеновский снимок стыка, по которому можно сделать вывод о его качестве.
При расшифровке снимков мы выявляем внутренние дефекты, обнаруженные дефекты и описываем их в заключениях. Производим оценку качества сварных соединений.
Тут необходимо отметить, что наличие дефектов в сварном соединении не всегда свидетельствует о плохой работе сварщика. На их появление могут повлиять факторы, не зависящие от того, кто непосредственно делал стык. Положительное же заключение дефектоскописта – гарантия того, что сварное соединение надежно проработает отведенное ему время. Юрий Грига, Кирилл Мамонов, Ямбурское месторождение.
Non-destructive testing. Magnetic particle inspection. The magnetic particle examination is an excellent method to investigate near-surface defects in ferromagnetic materials. This video shows the basic principle and the practical procedure. The material tester gets the machine ready for use and inserts the test piece between the two poles of an electromagnet. Then she takes a bottle with a suspension of magnetic particles, turns on the electromagnet with a foot switch and applies the suspension of magnetic particles onto the test piece. Already in daylight, dark lines are visible on the surface. The lines can be seen much better under ultraviolet light and particularly well at darkening the daylight. The suspension contains pigments that cover the magnetic particles and fluoresce under ultraviolet light. The particles run off in areas free from defects and they are attracted and clustered near defects. This workpiece shows a whole array of cracks. The basic principle is to magnetize a ferromagnetic workpiece parallel to its surface, as shown in the sectional view. If the workpiece is free from defects, the magnetic field lines run within the workpiece and parallel to its surface. In places of magnetic inhomogeneity, for instance near cracks, the magnetic field lines will locally leave the surface and a leakage field occurs. Now, if a suspension of ferromagnetic particles is applied onto the test piece surface, the magnetic particles will run off at defect-free areas. In places of leakage fields, the magnetic particles are attracted and clustered together, thus indicating the place of the defect. The method works best using a pigment which covers the magnetic particles and shows fluorescence under ultraviolet light. Even cracks can be detected that are not open to the surface but just below it, as long as they are not too far below the surface. But one precondition must always be fulfilled. The magnetic field lines must be perpendicular, or at least at a certain angle to the defect. Otherwise there will be no leakage field and the defects remain undetected. Our test sample has been magnetized in horizontal direction. The magnetic field lines run horizontally. This is the reason why cracks in vertical direction are visible particularly well. To make sure to detect all near-surface cracks, one has to magnetize the sample once more and best perpendicularly to the first time. To do this, the material tester switches the machine over to the current flow method. A high electric current flows through the sample, generating a circular magnetic field. Now the cracks in horizontal direction can be seen very well. The tested sample is a hardened sliding guide. The cracks have been formed during the hardening process and the subsequent grinding operation. Still another test piece has to face the magnetic particle inspection, a section of a large gear wheel. The same procedure again. Placing the gear wheel between the magnetic pole pieces, magnetizing and applying magnetic particle suspension. Already in daylight, there are indications of cracks, and again, they are best visible under ultraviolet light while darkening the daylight. The visible cracks are so-called fatigue cracks. They have been generated during the operation of the gear drive, due to a mismatch of the gear wheels.